The good old bipolar junction transistor, or BJTs. These are the first transistors that we'll look at. So we talked about this last class about a transistor basically operates on the same principle as a water valve, right? So we got a power source somewhere. Of course, in a water system, the power source is the pump. And then we've got a water valve, and what does a water valve do for us? Huh? Well, yes, but technically it's what we use to control the flow of the water, right? And we can turn it all the way on, or we can turn it all the way off, or we can put it somewhere in the center, right? And that's the same thing true with a bipolar transistor. We can turn it all the way on, which means it acts like a closed switch. We can turn it all the way off, which acts like an open switch, or we can turn it all the way somewhere in the center where it acts like a rheostat. So transistors are electronically controlled current valves. So the difference so I've got an ice maker on my house, on my refrigerator, and I don't have to turn anything because that water valve is electrically controlled, right? You understand? I go up there and I get my glass out and I push it up against the little arm there, and all of a sudden it starts pumping ice out into my glass. So some water valves are electrically controlled. I got a washing machine at my house. I go up there and flip. Well, I don't wash clothes. Very, very seldom. I'll go in there and, put clothes in there, put all the stuff in there, and I turn a switch to hot, cold, and all that other kind of stuff. And those water valves in that one are they're electrically controlled, which means it takes no human intervention to run the valve. Now we have to turn some knobs. But a transistor is an electrically controlled current valve. We have two categories of transistors that we're going to look at. We're going to start off with the bipolar junction transistor, and then we'll move into the FET, which is the field effect transistor, which a lot of people call the FET. Are we okay? And what we do is construction. It's called bipolar because we basically have two p-n junctions. Construction of the three dope semiconductor regions that produce a p-n junction. So what we have is we have two p-n junctions. And this is why it's called which usually stands for two, right? Bipolar. We have three connections that we make to the transistor, and these leads are given a name. So just because you see a device that's got three leads coming out of it doesn't make it a transistor, but to be a transistor, it has to have three leads, right? So what we'll do is we'll come up here and we'll have some type of a package that the transistor is going to be in. And we got all types of packages. I don't know if I've got them on there. And then we'll have three connection points that we can make to this thing. One of those are going to be the emitter, one of them's going to be the base, and one of them's going to be collector. Does that make sense? Now, what they do is, and this is not exactly a good picture, but it works pretty good to help explain it. What we have is we have one region. We have two types of bipolar transistors. We have one that we refer to as a NPN. And then we have another one that we refer to as a PNP. And you can see how they got the name. So the NPN has a P material sandwiched between two N's, and a PNP has a P material that's sandwiched between an N material that's sandwiched between two P's. Y'all understand that? And this is how it gets its name. The one in the center, which is the little tiny small one, and this is a lot bigger than it is. It's an extremely thin junction that's in the center. This guy right here is what we call the base. the base is your valve control. So what we do with the base is we control the size of the orifice in this valve. So that's what you're doing when you do a water valve. There's an orifice in there, a hole in there, or something. And what you're doing is you're controlling the size of that hole that the water has to be pushed through. And if you control the size of that orifice, then what are you doing? You're controlling the flow of the water. And that's the same thing true with the transistor, the bipolar transistor. Let's rephrase that. That's the same thing true with all transistors, whether it's a bipolar junction transistor or whether it's an FET. It's just that we control the size of the orifice that's letting the current go through. We control them using different methods. Are we okay? And the base is going to be lightly doped, so there's not many majority carriers, or it's going to be medium, I guess. The collector is going to be lightly doped, and then the base is going to be heavily doped. And what do we dope a semiconductor to do? What are the reasons for doping? Somebody missed that on their test. This increases conductivity, but not only does it increase conductivity, it gives us the ability to control the conductivity when we combine an N with a P, right? You understand? But if I just got a piece of P material, does it carry a P charge? If I've got some P material holding in my hand, does it carry a P charge? It's a simple question, guys. Yes or no?
Yes. No. Yes.
No. It doesn't carry a charge at all because your electrons and your protons still match, right? You understand? It's just that now we've got a bunch of holes that's floating around in there that can be moved. Y'all understand that? And an N material does not have an N charge. It's just that it's got a lot of free electrons in there, but the electrons and the protons still match. Now, when I form those things together, we create ions because that's when they drift across and create that barrier voltage, right? But that's only when we combine these two things. So what you see here is we got two junctions, and that's why it's called bipolar. We have a p-n junction between the collector and the base. So we can check this with an ohm meter. So I can come over here and put my meter on the diode scale, right? And I can put my black lead toward the N and my red lead toward the P. And if it's a silicon transistor, then it's going to measure about 0.7 of a volt. If I flip the lead around, it's going to measure extremely high, right? Most digital multimeters will register it as an overload. If it's a germanium transistor, and I was looking at a video in there, and that's what they said. They said they're made out of silicon, and they're wrong because we have germanium transistors too. Germanium transistors have the ability to switch a lot faster than silicon because it has a lot less potential, but they have very poor temperature characteristics. And then and this is the way we check a transistor. We check it with an ohm meter. And if I come over here and put an ohm meter right there and put my black lead toward the N and my red lead toward the P, it's going to measure approximately 0.7 of a volt if it's silicon. If I come over here and put my meter across the emitter and the collector, what do you think it's going to measure? Well, show me two p-n junctions that I'm forward biasing. So my red lead would be on an N, which is jerking it that way, right? My black lead would be on the E, which is putting it that way, and sandwiched in between, I got a P that's not doing anything, right? So when we measure collector to emitter, we should measure extremely high ohms, extremely high in both directions. And this is the way we check a transistor with an ohm meter, just like we do a diode. Right? So no matter which direction I put the lead, so let's say I put the black there and I put the red there. Well, the red is still pulling the E's that way, the electrons that way, right? So we still have, so you should, when you check your collector to emitter, you should have an extremely high resistance. Most digital meters will show it as an open. But you got to be careful. These Sperry meters, they go up to over 3 volts, and they just show you a reading. So what you need to do, of course, on your meter is hold your meter up in the air and put it on the diode scale and see what it shows you. And that's what it's going to show you when it sees a reverse bias junction or on a bipolar transistor when you measure between the base and collector. So we check these, we check this just like we do a diode. So we forward bias and we flip it around and make sure that it doesn't measure the same in both directions. So it should measure real high in one direction and real low in the other if I'm going between the base and the collector, right? Understand? And then I come over here and do this and make sure you swap your leads around just like you should on a diode, right? You understand? Because it is supposed to measure low on one side and high on the other, right? So here to forward bias this junction, I would have to put my red lead on the collector and my black lead on the base, and that way I would read depending on what type of transistor it was. And then if I flip it around, it's going to read real high, right? You understand that? And if I read between the base and the collector, it's still going to measure real high. If it's good. If it's bad, it might measure the same in both directions. So that's why you need just to flip it around each time. So how's this thing going to work? Well, what happens is we come over here and the base is extremely thin. So what we do is we bias. And what is bias? We've already talked about that. You need to be able to define what the term bias means in electronics. Close. It's a DC voltage applied to a semiconductor. That controls or determines its electrical characteristics. So bias, a DC voltage applied to a semiconductor that controls or determines or sets its electrical characteristics. All those would be good definitions. So to make a transistor operate as a current valve, we're going to have to bias it. Y'all understand that? Now, the way we bias the transistor, let's see what else is there. Because NPN is the most commonly used, and we'll talk about that. The transistor works as 2 diodes with a two PN junctions. The emitter is heavily doped, the base is lightly doped, excuse me, I got that wrong, and the collector is what? Moderately doped. Everybody okay? The PN junctions joining the base region and the emitter region are called the base emitter junction. And then the other junction is called the base collector junction, right? So we give that junction a name. We need to understand that because that's what we're going to talk about when we start talking about how we bias this thing. So here's our 2 electronic symbols. And what determines the symbol is direction that this arrow is pointing right here. So this arrow right here is not pointing in. So as soon as you say not, you're identifying the emitter. So this is not pointing in. So that's the symbol for what? Now I come over and look at this arrow. What is it? It's pointing in. So it's a PNP. So that's as simple as I can possibly make it. You look at the arrow and see which way it's pointing. If it's pointing out, then it is not pointing in. Right? You understand? And we bias these things different ways to determine, so the arrow points toward the end. Are you okay? In order the transistor to operate properly, the 2 p-in junctions must be applied with an external DC voltage to set the operating conditions, and we call this what? Bias. It has to be biased. To make it work, the base emitter junction has to be what? Has to be forward biased, and the base collector junction has to be reverse biased. Y'all understand? Since the base emitter junction is forward biased, even though the base collector is reverse biased, this condition is called forward bias. Because this is what's required to make the transistor operate. Do y'all understand? Yes or no? The forward bias from the base to emitter narrows the base to emitter depletion region. The reverse bias from the base to collector widens the base to collector. And this is what we got to look at. So let me throw up a diagram right here. So what I've got is I'm going to come over here. Of course, we're going to have to put resistors in here, but think about this. So let's say it's an N, a PN. Then what I'm going to do is I'm going to put an extremely high positive up there. And what it's going to do is it's going to start sucking these things where? It's electrons in there. It's going to start sucking these electrons because it's an N material. Okay, you understand? So I've got this big old positive potential up there sucking every electron up there that you can possibly get to. Y'all understand? Then what I'm going to do is I'm going to make this one negative in respect to that. So we're not going to make it negative right now. Let's just put it to common. Of course, common is negative with respect to that big old power supply up there, right? Y'all understand? Then I'm going to come over here and I'm going to put a small voltage right there. In fact, to forward bias this junction right here, if it's silicon, it's going to take about 7/10 of a volt. As soon as I get 7/10 of a volt, then that junction right there is forward bias. As soon as it's forward bias, then we got all these electrons over here. I mean, they're going to come up here. They're going to start flying toward that. And you got this little tiny base that doesn't have hardly any majority carriers in there. And it hits this little old tiny base, right? You understand? And then it says, okay, I got 2 ways I can go. I can go this way toward that little tiny P, or I can go up to that big old plus up there that's sucking everything up there, right? So what's it going to do? Yeah, 99.95% of these electrons are going to fly right through that base because it can't make that turn, right? And we like to say, okay, I got a water hose, right? And I come over here and punch a little tiny hole with that water hose. Where's 99% of the water? And the little bit of water starts squirting out there because I have a difference in potential between that little hole, right, and the outside pressure. But the biggest difference in potential is where? On the dang end of that hose. So what happens? 99.9% of the water goes to the lower pressure, right? And just a little bit does what? Squirts out that little hole in the hose pipe. And that's the same thing true here. So that collector up there is going to be a real high potential opposite of the collector. And it's trying to suck these electrons, anything it can get, right? You understand? So a very little bit of current goes where? Out the base. So here we go. It goes. And there's our valve. I just turned my valve on. And just a little bit goes where? That direction right there. Okay, so that turns the valve on. Now what determines how wide the valve is how many electrons we're sucking from the emitter. And that is directly controlled by the amount of, so this would be the base, this is going to be the emitter, and this is going to be collector. And we usually abbreviate those with lowercase letters. So the more current I pull into the base, then the more current I have that flows through the collector and emitter. So what I do, once we turn the valve on, I control the amount of current flow between the emitter and collector with base current. And it is directly proportional. It don't mean they vary. So if I double the base current, my emitter and collector current double. If I half my base current, my emitter and my collector current halves. So what we can do is we can do what? We can control the size of the valve by controlling the amount of base current. But I don't get any base current at all until I get up above that about 0.7 of a volt, right? So if the base is less than 0.7 of a volt, the transistor is good. It is off. Well, we don't call it off. We call it cut off. The transistor's in cut off, right? Of course, the way it works now is that I could eventually keep adding more base current and more base current, and eventually we would burn the transistor up. Okay. So what we have to do to set the bias is we got to put some resistors in here somewhere, right? It's just like a diode. You know, I come over here on a diode, and I came over here and did this. Let's say I come over here and put it directly across the power supply, and I forward bias it. Somebody's going to give up, right? You understand? Because as soon as I get up above the VF of a diode, it acts like a closed switch. So here we have a short circuit. And when we have short circuits, somebody gives up, right? You understand? So either the power supply can't handle that current, or a wire burns up, or the diode burns up, whichever one gives. But somebody's going to give up first when we have short circuits. Somebody's got to give up, right? So that means if I came over here and applied enough base current, so I could, if I don't do that, you know, I could come up here and control it, because now it's going to act like a rheostat, right? Y'all understand what a rheostat does? What's the difference between a rheostat and a potentiometer? Good, but which one's which? Yeah. So rheostat controls a current, right? Now, of course, the byproduct is going to be a voltage, but a potentiometer is what we call a variable voltage divider. If you learned about voltage dividers in DC, and you were supposed to. But we have fixed voltage dividers, and then a pot is a variable voltage divider. So what we're going to do is we're going to take this guy, and we're going to come over here and I'm going to put a resistor at least right here up in the collector. And generically, we refer to that resistor as RC. Let's say we put 12 volts DC up there. And then I'm going to come down here and put this to common. And since I've got a positive on the collector, then this would be the way we would bias an NP N transistor. And how much current flow would I have? I have no base current. If I have no base current, I have no collector current, or I have no emitter current. Now that's not true, because this is not an open switch. It is a semiconductor, but it's going to be an extremely high resistance, right? So we're talking about current flows that down in the microamps or the nanoamps, because there is a path current can get through there. Y'all know there's current flow through insulators, right? Because there's no such thing as a perfect insulator. It's just that the number of electrons in there to be able to push are so small, they're bonded so strong together that almost no current moves. So if I've got a path for current to get through, and I apply a difference of potential, then current is flowing. So I can take a little 1.5 volt battery, and I can take my two fingers and touch the two ends, and there is current flow through my body, because there is a path through my body, right? And I am not an insulator. It's just that the current flow is so small that we cannot even understand it, right? You understand?
What about like a 12 volt battery?
12 volt battery, you know, you can't fill a 12 volt battery. Go out there and touch both the leads on your car. How many times have you done that? How many people touched both the power, positive and negative lead on their battery on their car? Why don't it key? I mean, that sucker's got 200 or 300 amps available out there. Why don't it key? Yeah, you're probably in the rain. Was it raining or in the summertime?
I was working on something.
Well, it's very unusual. Huh? Yeah, if you got cuts on your hands, that's one thing. Your skin has a really good resistance on it.
Yeah,
I felt it before, but it's been raining or it's been like in July or August, but it's still not enough current to key. What's considered to be the lethal voltage? Anybody know? About 50 volts. Yeah, anything above 50 volts is considered to be lethal. Anything below 50 volts is not considered to be lethal. You have current flow through your body. Once you get around 10 milliamps, you can feel it. So if your body resistance gets down enough to get 10 milliamps, which is not much, and you're going to be able to feel the current flow. It's going to give you a little tingle, but it's not a shock. I mean, it's not near lethal. So a 12-volt battery can't kill you. Well, that's not true. It can blow up on you. It's got hydrogen. You know, the byproduct of lead, of mixing lead and acid is it creates hydrogen. And you know, hydrogen is what? Very explosive. And it scares me to death watching people out there with their jumpers and they put them on their battery and they're going and they're sparking all over the place. Jeez. They're living by the grace of God. So what you're supposed to do is hook up your black lead first and then hook up your red lead somewhere else away from the bat. I mean, your red lead first and then hook up your black lead somewhere away from the battery. Like on your bumper or on a big metal chunk of your car, of your engine. But, don't do that. I've seen the results of a battery explosion and it wasn't pretty. I didn't see it happen, but I saw the guy a few years after that. So right now we'll measure, if I measured across the diode, across the transistor, what would it measure? Well, any base current. Y'all don't know that? If it's like if there's no base current, the transistor is acting like an open switch. So that means I could come up here and substitute for this circuit right here. And there's my transistor. Up here I've got 12 volts. What would I measure across the switch? Any open in a series, so to get voltage drop across this resistor right here, V is equal to I times R. V would be equal to 0 times, let's say it's 1K, 0 times 1K. So what would the voltage drop be across that resistor? Okay, if that voltage is if that resistor is dropping 0 volts, that means I have 12 volts right here. If it's dropping 0 volts, then I have 12 volts right there. Y'all understand that? So in a series circuit, if you got an open, the entire applied voltage appears across the open. Why? It has no current flow in the circuit. If there is no current flow in the circuit, nothing in the circuit is dropping voltage. So all your wires in the whole circuit are acting like straight pieces of wire. And it gets up to that open and it appears across the wire. Open. So if I go over here to this light switch and I measure across these switches right here, what is it going to measure? The ones that's running these lights. What is it going to measure?
Sorry, no.
I hope not. How can the light work if all 120 volts is being dropped across the switch? Okay, Kirchhoff's voltage law says the sums of the voltage drops in a circuit have to equal to the applied voltage. Well, if I've got 120 volts across the switch, what's left over for the lights? Power is equal to V squared over R. I have no V, I have no what? Power. So what's the voltage? What voltage should you measure across a closed switch? 0 volts. A closed switch is supposed to have no resistance, right? So here I come over here, and I got V is equal to I times R. So I got V is equal to 15 amps times 0 ohms. How many volts do I have dropped across a closed switch? None. So you go across that switch over there and you measure it with a voltmeter, you're going to measure 0 volts. And you're going to say, well, there's no voltage there. Right? You understand? And there's ground in there. You stick your hands in there. You get your fingers up against that ground running through there because the yoke is grounded, so the yoke can't get a charge on it. And you're going to get your butt what? Shocked. If I measure across the open switch, it's going to measure what? It's going to measure the applied voltage. Y'all understand that? That is a basic law that you need to understand, because if you don't, what's going to happen? You're going to get your butt shocked. You get across some high voltage, like, 200 or 300 volts, you're going to get your butt killed, right? You understand? Or you're going to get burned real bad. We had a guy, went to work for a company, and he was playing around with a light, He got his hand caught between the light and the ground and burned his hand real bad. He got out of the trade. He quit that day. Quit the job. But whose fault was it? It was his. So if you don't understand what you measure across a closed switch and what you measure across an open switch, then let me know where you go to work, and I'll make sure I don't go to work out there with you, because you're going to get somebody killed or you're going to get yourself killed. So what should we measure across any type of closed contact? We should measure pretty close to 0 volts, right? What should you measure across an open contact? You should measure pretty close to the applied voltage. Now, if it's a true contact, then it will be an open. But a transistor is not a true open, right? You understand? There is a path. So I might have 12 volts up here. When I measure across this transistor, I might measure 11.9999 if my meter would measure that. Most meters will measure that at 12 volts because there's going to be a current flow through it, but it's going to be so small that odds are you can't even measure it, right? Okay, y'all follow me so far? Okay. So let's say I come over here and I hate when y'all answer that. I do that. That's just me, because I don't want y'all to get out there and get yourself hurt. Say, don't you hire one of those Lawson State people? They don't even know what you measure across an open switch. Nah. We've had them call before. We had one company called and said, it's before Rhett's Electronics, they used to be our competition before IT&T opened up over there. And I had an employer called and said, ITT sent some guys out here for this job and they didn't even know the resistor color code. That's true. And they didn't hire them. That's not exactly true. You could go to Radio Shack and you could buy this little color wheel. So you put your colors in there and it gives you the ohm value. And that's what he says. He said, don't you send anybody over here that's got to use that color wheel to know the color code for resistors. So they didn't hire anybody. I said, if we send you somebody, I'll send you somebody that knows the color code. So we stress that because, you're in electronics, right? Y'all understand that. Most of y'all in here are now IoT. And that's industrial what? Electronics. And knowing the resistor color code would be part of electronics. So you need to know it. So don't come and ask me for a resistor unless you know the color code of the resistor you want. Because as soon as you ask me, what am I going to say? What's the color code? Okay, so when I come over here now, and I put a base lead over here. So what we're going to do is we're going to come over here. Let's do this right now. So I'm going to come over here, and I'm going to put a rheostat right there. And I start adjusting it. So right now, let's say I start off with the maximum, and it's a big resistor. So let's say maybe 10K or so. and I adjust it all the way to 10K. Well, there's not enough current flow through this to get that 0.7 volts that's required to do what? Turn it on. So this voltage right here would probably start dropping a little bit. But let's say I come over here and start turning this pot down, and then I exceed the 0.7 volts, and then all of a sudden we start having current flow through that way, right? And as soon as I start having base current, I'm going to have emitter current and collector current. But the emitter current and the collector current is going to be greater than the base current that caused it to flow. So let's say RC is equal to 1K. And let's say I come over here and I cause 1 milliamp of current flow here. Now 1 milliamp of current flow over there might have been caused by 10 microamps of current flow here. Because we get a current gain, right? You understand? These guys here give us a big current gain. It's just like last class when we was using those little old photo resistors and the little thermistors to control the speed of a DC motor. Well, a thermistor can't control the speed of a DC motor, but it can provide a little current that I can put into the base of a transistor, and the base of the transistor is going to give me a current gain, right? You understand? So what would happen is my resistor up here, 1K, 1 milliamp, it's going to drop 1 volt. So what's the voltage drop across my transistor going to be? This is no approximate, it's Kirchhoff's law. Kirchhoff's law says the sums of the voltage drops in a series circuit have to equal to the applied voltage. So this is going to measure 11 volts. I increase my current flow, I come over here and I put 20 microamps. I double the base current, what's going to happen to the collector current? It's going to double, good. So it's going to go to 2 milliamps. This resistor right here is going to drop 2 volts. This transistor is going to drop 10 volts. Everybody understand that? So now the potentiometer is acting like this. The transistor is acting like this. And I'm taking my output across the transistor right here. But what's controlling the rheostat? Good. The base current. So the more base current I put into it, the rheostat goes down, which means what? Huh? It means that the rheostat's going to drop less voltage, and the fixed resistor has to drop more, right? But the sum of the voltage drops between this resistor I'm calling RC and the transistor will always add up to be the what? The applied voltage, because of Kirchhoff's voltage law. Okay, so I keep going, Let's say I get up to Let's say I get up to 12 milliamps. Of course, that would be, what, 120 microamps over here. Well, explain to me what's going to go on now. So I calculate my voltage drop across my resistor. So VRC would be equal to 1K times 12 milliamps. VRC would be equal to 12 volts. So what's the voltage drop going to be across the transistor? It's going to be pretty close to 0 volts. So now we've replaced that resistor over here. We've replaced it with a switch. Or we've replaced it with this guy right here. Basically, right? You understand? It's acting like a closed switch. We call this saturation. So we can operate the transistor in cutoff. We can operate it in saturation. So cutoff, it acts like a open switch, right? All the voltage would be dropped across the transistor, right? You understand, because it's acting like an open switch. And that happens if we get that base below 0.7 of a volt, or approximately 0.7 of a volt. You know that when you did your diode curve, it came over here and started conducting around 0.6. But if I'm down in here, you know, we say it acts like an open switch. Now, it's not an open switch. Y'all understand that? There will be a small, I might measure a little bit of voltage across my transistor, but it's not going to be enough that most meters that we have would measure. And then if I put enough base current in there to cause RC to drop all the voltage, right, you understand, to cause the collector current to get so high that RC drops all the voltage, then the transistor's saturated. Let's say I take my base current over here to 300 microamps. What's going to happen? Well, nothing's going to happen, because once that resistor drops the applied voltage, I can keep pumping base current into this sucker, and it's not going to do any good, right? It's usually like a water valve. A water valve usually gives you the maximum flow before you get it turned all the way on, right? Have you ever noticed that? You over here turning on your sink and you get maximum flow, and you keep turning that knob. It don't change the flow anymore, because you got the maximum flow that's being provided by your water system. Once you get the maximum flow that's being provided by your system, then you can't get any more flow, right? No matter how big you make the valve. So we can't make the valve any bigger once we saturate the transistor. Well, what happens when we operate it between saturation and cutoff? So in digital, if you heard about digital, we use these transistors all the time. And that's what we do. We operate them between saturation and cutoff. Because in digital, we're dealing with ones and zeros. But when we say ones and zeros, you know, I've got to represent a 1 and a 0. And we can represent a 1 and a 0 a lot of different ways. You know, but a computer can't just say, I can't say 1 and 0 to a computer. It's got to represent it with either a current, or it's got to represent it with a voltage, right? You understand? And the most predominant used representative of a 1 and a 0 in digital is a voltage. So this works perfectly. These transistors work perfect, right? I can flip them off and on, off and on, off and on, and get a 1 or a 0, but I can electrically control this. But if I operate it between saturation and cutoff, then I end up with the transistor acting like this. And we call this the active region. Some people refer to it as the linear region, because this will be linear. That base current and that collector current vary at exact ratios. And if you know that ratio, then you can, if I can measure the base current, I can calculate the collector current as long as I'm in the active region, right? You understand? Or if I know the collector current, I can calculate what base current would cause that to run at, because that ratio is a linear ratio. I mean, it's almost perfect. But it's going to vary with temperature. So the ratio between the base current and the collector current varies with temperature. So we'll talk about some of the things we do to help get rid of that variation with temperature. So we got different ways we can bias the transistor so we can just about ignore temperature. We can ignore beta. We can ignore this ratio. Is everybody okay? So this is real neat. I've got a current valve that I can operate as a switch, you know. And a lot of water fountains, you go up there and you hit a button and it turns the water all the way on. You let go of the button, it does what? Turn it all the way off. But you can go out here to this water fountain in the hall and you can press it all the way down, it turns it all the way on, right? You let it go, it turns it all the way off. But just push on it lightly. And you can say you can control the flow of that water coming out of that valve. And that's what we can do when we're operating in the active region. So we got 3 regions we can operate a transistor. Now notice I didn't say a bipolar transistor. This is also true for FETs. We got 3 regions we can operate these transistors in. We can operate them in cutoff. Of course, if I operated a transistor in cutoff all the time, I would just not even hook something up, right? Or I can operate it in saturation. Normally, we switch it between the two. So if I wanted to control a light bulb, you know,
When it's in saturation, that's when it's.
acts like a closed switch. It is not a closed switch. It will drop, and we'll look at when we look at the specifications. One thing they're going to give us is the saturated voltage drop. What we should expect that transistor to drop when it's saturated, and it's going to be less than a volt. So we're going to be down in the watt, in the millivolts. And when you're down in the millivolts and you're dealing with volts up here and millivolts down across the transistor, most of the time we just kind of ignore the millivolts, right? And it's going to be small. Yeah, the active region, it acts like a rheostat. And we're talking about, it's the valve, not the base, it's the connection between the collector and the emitter. So when the transistor is cut off, it is not a closed switch, it acts like an open switch. When the transistor is in its active region, it acts like a rheostat. I think that's the way it's done. Don't whip me up on that. And we operated in saturated. It looks good, doesn't it? It acts like a closed switch. And we use these things all the time. You know, if you think about just your car out there, you know, switching between saturation and cutoff. You know, you got a little old tiny button you press on your steering wheel. You know, you engage your cruise control. There's no way in the world that little button is going to throw in all the electronics that control cruise control. Right? So what you're doing is you're using a transistor out there, some type of transistor that you're causing it to either saturate or cut off. Makes sense? Your headlights. Most of you got a little old tiny button on your car, you turn your headlights on or off. Mine's up on my control on one side. And there's no way in the world I'm going to pass the current that's required to turn on your headlights and your parking lights through a little switch that comes through something that's hooked up to a slip ring, right? You ever took a steering wheel across, you got all these slip rings in there, and you got these brushes riding up against them, and you're trying to push all those currents through something that's in motion, but very little current's no big deal. So what you're doing is you're saturating transistors. When you flip your lights on, when you change and when you turn your lights off, you're switching those transistors out there between what? Between cutoff and saturation.
I don't know, some old cars, they just got a switch.
Yeah, but I'm talking, you're right. In the old days, we had a big old foot thing in the forward. And the light, but it was a big old switch. You ever take one of those suckers apart? Now we're in an electronic world. There's very few things in your car that switch is directly controlling. Yeah, you got an old 55 Chevy, you're going to have a big old foot switch down there. And I'd be in trouble because that's my left foot. I wouldn't be able to do what? I mean, I'd have to be one of those guys that rides with the lights on bright all the time. But now they moved just about all the controls on your car except for your gas pedal. You know, if you got an automatic transmission, into the what? Into your steering wheel. You know, you can change channels on your radio. You know, you can turn your radio on, you can turn them off. You can turn your lights on and off from your what? From just about on your steering wheel. Now, just about all that stuff's on your steering wheel because what they're trying to do is prevent you from doing this, you know, to try to get into the controls of your car. And what you're doing, of course, is your volume control is probably using the transistor kind of like a rheostat, right? And then changing the channels would be just to saturate a transistor and turn it on and turn it off. And And these guys right here, what's nice about them is we get that current gain out of them. So it takes very little current to control a bigger current, a much bigger current, right? You understand that? And we'll talk about, so, and that's the specification that we get is the current gain we get between the base and the collector. Now the problem is what goes on is when we forward bias this thing, and we'll look at the NPN, is that I need to put a big positive up here, right, you understand? And then I need to put a little positive right there. And then if this right here is positive, it's got to be even littler positive. And we're going to do that before long. Now, as soon as we forward bias it, then we have current flow. We have a little bit of current flow that way. And we have a heck of a lot of current flow this way, right? You know, because you got your druthers, you hit that little old thin base region, and you got this big old pot in your electron, you got a negative charge, you got this big old positive up there doing what? Sucking electrons, or holes if we're dealing with a PNP, sucking those. Hold on a second. What do you got? Things in the wrong class. I should stop and talk to you. He said, I'm in the wrong class. We got these things sucking these electrons. So we have emitter current, which is what we're going to refer to as IE. And then we have base current, which we're going to refer to as IB. And then we have collector current, which we're going to refer to as IC. And Kirchhoff's current law says the sums of the currents into a junction have to equal to the sums of the currents out, right? So IE would be equal to IC plus IB. So IE is always your biggest current in the transistor because it handles everything, right? And then IB would be equal to IC minus IE. And then IC would be equal to IE minus IB. So this is your main formula. If you understand that one, then the other two formulas can be derived from that, right? Just by moving things around. So it means if I measured my emitter current, it's going to be the biggest current in there because it's handling both what? The collector current and the base current. Now, when we get into calculations, we're going to kind of ignore the base current. I know the base current has to be there because if the base current wasn't there, then I would have no emitter current and I would have no collector current. So when we get into doing most of our calculations, we're going to assume that IC and IE are approximately equal to each other. They're not equal to each other, they're approximately equal to each other. It's just that the base current is so small that normally we can ignore it. Very simple formulas. This is just Kirchhoff's law. Y'all understand that you learned in what? DC. You didn't learn this in AC because you really didn't get into Kirchhoff's current laws until you got into parallel circuits. And you don't get into parallel circuits in the intro to electronics. You get into those when you get into DC. And you're supposed to have DC, which that guy right there I've never seen before. I should have stopped. I'm sorry. I hope he can find his class. This is a program called Electronic Workbench. And Electronic Workbench allows us to simulate programs. So out here I got an NPN transistor. And then I've got a meter. This is an ammeter that's measuring the total current flow into the transistor. Then I have a meter here that gives me my, this will give me my collector current, I'm sorry. Then I have a here that's going to measure base current, and then I have another one that's going to measure the emitter current. And I don't know what we got. Let me turn on my. So right now I'm measuring 12 volts across my transistor, So that means the transistor is what?
Which one is it?
This guy right here.
It's cut off.
Yeah, but it's measuring 38 microamps. So we're actually measuring the basically the leakage current. But I'm looking at my voltmeter. Here's my voltmeter on the right, and I see the voltmeter here is in red. And we notice that the transistor's dropping 12 volts. If the transistor's dropping 12 volts, is it saturated, or is it cut off, or is it active? It's in cutoff. That's exactly right, because it's doing what? It's dropping the entire voltage. Now what I'm going to do is I'm going to come up and start giving us a little base current that's going to cause something. Right now we're only getting 384 nanoamps. Microamps. And notice the base current goes up. As soon as we start getting base current, then notice the emitter current starts going up and the collector current starts going up. But notice the emitter current is 123.1 microamp. The collector current is 121.9 microamps. And what's the difference? Well, the difference is this current right here. So odds are if you add this current to that current, it should come up to give you pretty close to what that is. It might not be because it's a simulation. Are we okay? So I'm sorry, if I subtract this, if I add this current to that current, it should come up and give me this. So I'm going to come up here and start, so we're now in the active region. See, I'm going to increase the base current, and you notice this every time I increase the base current. So over here, I'm getting 1.158 milliamps, but what did it cost to get that? It only cost me 11.8 microamps to control the valve. So we're getting a pretty big current gain. How do we calculate current gains, by the way? By the way, normally the collector does the work. So normally, this is not true all the time, but normally the collector current does the work. So here's my load, and what's it connected to? It's connected to the collector. So when we start calculating the current ratios, what I'll do is I'm going to take IC and divide that by IB, and that will tell me, so anytime we calculate any gain is always calculated with out divided by in, right? You understand that? That's a gain, right? You understand? Everybody okay? So we're going to use IC as my output current. So I've got a 1.148 milliamps on my collector current, and I've got 11.48 microamps on my base. So what's the current gain of this transistor? By the way, gain has no units. And people have so much problems with that. It's just like if I say I'm going to triple your salary, you say, well, that's great. I'm going to get a $3 an hour raise. Right? You understand? But I'm paying you $50 an hour, and you're expecting $3 because I'm going to triple your salary. So that's a gain, right? You understand? So if I raise your salary, I don't say $3. I usually say we're going to give you a 25% raise, you know. And then, of course, you can use that gain to calculate how much money that is. They never tell us how much we're going to get in dollars. They always tell us we're going to get so much percentage, which we hadn't had in a while, by the way, probably 7 years. So what would be my current gain, my collector to base current gain for this transistor? Good gracious, folks. So what was IC? I can't write on the other one. So my gain is going to be IC over IB. And for reasons we won't talk about, normally what we're going to refer to this is beta. But they don't call it beta in the data sheet. And we abbreviate it with the Greek symbol beta. And beta is calculated with IC over IB. So what did we have? My beta would be equal to
1.148.
You did exactly what I told you not to do. So I'm getting 1.148 milliamps out, and I'm getting 11.48. It's taking 11.48 microamps to get 1.14 milliamps. There's no way in the world you're going to get a 1 out of dividing 10 to the minus third by 10 to the minus sixth. There's just no way in the world you're going to get a 1, right? You understand? Because my little number's on the bottom. So I know it's got to be a lot greater than 1. Everybody get their calculator out and calculate this for me. And I want you to write this down on a piece of paper, and I want you to bring it up to me. IC over IB. Write your name on it. Bring it up to me. By the way, some of y'all, and I hate to say this, some of y'all, there is no way you're going to be able to use me as a reference for a job if you can't get to your job on time. Y'all understand that? This class starts at 9 o'clock. My mentality is, and I've been in the military, and by George, if you show up at exactly the right time in the military, you are late. U.S. Steel, if you showed up at exactly the right time your shift was supposed to start, you are what? Late. So what I've learned over time, if you show up on time, you're late. Y'all understand that? So I'm supposed to get here at 8 o'clock. If you come by here and my car is not out there before 8 o'clock, then something is drastically wrong. Either I'm somewhere on campus doing other stuff, right? You understand? Or I'm sick or I'm dead. That's the only reasons I'm not here before I'm supposed to be here.
Except for I see you.
IB. So if you can't show up to my classes on time, do not use me as a reference on your job application. Do not even ask me. And I believe Nancy would tell you exactly the same way. Do y'all understand what time this class starts? And this is a required course. If you fail this course, it's not like an elective where you can take something else. You've got to take this class. We offer this class maybe once a year at days. We offer it once a year at nights. So that means if you can only come days, then when's the next time you're going to be able to take this class? Probably next spring, right? You understand? I have never seen anything like this since I've been teaching in 1982, where I got 11 people in a class, and I get here and there's 2 people here when the class starts. I've never seen anything like that. If you'd have been here the last dean that was here, you'd be locked out that door. That's what he told us to do. He said when the start of the class time, lock the doors to your classroom. That's what he told us to do. So if you cannot show up for this class and get here before 9 o'clock, because I start lecturing at 9 o'clock, then do not use me as a reference. Do not ask me to use me as a reference. Because I cannot give you a good reference. And I told you the 2 things they asked, right? They cannot ask grades. They can't say, how did they do in the class? I'll say, I can't give you that information. The 2 things that an employer asks me is, do they show up on time? And how well do they work with others? That's the 2 big questions I get. And I don't lie. And I've talked to y'all and talked to you. I don't understand. You're training for a career. Now, I can understand why I might show up late for an English class, which I never did when I was in college. But good gracious, you're training for a career. And you're our reputation of this college, right? You understand? So what we got? Bring them up to me.
No, ain't from my name.
Yeah, you need to put your name on. Okay, gang, 10 seconds. If it's not up here, you don't get credit for it.
Oh, I got to put my name on.
Yeah, you better. You better. Put your name on. I don't know. Oh, sorry. I didn't see. I would put
You
something.
said 10 seconds, I just heard it.
That's good. All right, bring them up. If you can't see what's going on up here, what do you need to do? Need to move, right? Some of y'all got a big problem. Okay, so what we got is we got a gain of 1.148 milli divided by 11.48 micro. I've got 10 to the minus 6 on the bottom. I got 10 to the minus third on the top. We're talking about a number that's a lot bigger than 1 or 2 or 3 or 4, right? It's got to be at least what? 10 to the 6th on top, minus 6 on top, 10 to the minus third on the bottom, 10 to the minus third on the top, 10 to the minus 6 on the bottom. And you cannot just drop these engineering notations. I saw some of y'all that actually dropped the numbers. So this equals to 100. 100 what? That would be nice. That would be nice if I could put 1.4 microamps into something, 11.4 microamps into something and get 100 amps out. This is a gain. A gain has no units. Gains have no units. Absolutely no units, right? It's a multiplier or a divider, right? And it's just like when somebody says they're going to give me a 25% raise. Do they say I'm going to give you a $25 raise? Right? What do they say? They give you a percent, which and a raise is just nothing but a number. You would take that percentage, you would multiply it by what you're getting paid now, right? You understand? And then add it, and that would tell you what your salary is. So gains are not given in units. We have a way that we can represent extremely large gains that we call dB, but that's not a unit. That's just a way that we can represent large numbers. It's kind of like using exponents, engineer notation. So just because we say so many dB, and we'll talk about that, that's something we need to understand in this class, is decibels. But decibel is not a unit of measure. It's a way we represent extremely large numbers with very few digits. Just like we do engineering notation for, right? Extremely large numbers, extremely small numbers. With the problem with engineering notation is that your exponent, I'm sorry, I don't need to say that. So this guy here has a gain of 100. Now that I know the gain, I can say, okay, what would be the current flow if I come up here and make this go to? So if IC, so if the gain, which we call the beta, is equal to IC over IB, then what's IC going to equal to? It's going to equal to the beta times IB. Very simple formula. It's just gain. I mean, it's not a formula. It's gain, right? So if I come over here and put 14 microamps over here, what should I expect my collector current to do? So if I go to 14 microamps, what should we expect my collector current to do? Are we going to have to do the same thing again? So what did we say? So IC is equal to what? Now what did we just calculate beta to be? So that means IC would be equal to 100 times, what did I say the base current was? 14 microamps. So what would IC go to? Good. What would the voltage drop across that 1K resistor do? What laws are we using? I mean, all we're doing is just... So now I calculate the voltage drop across this guy right here, right? And it's a 100 ohm resistor. Oh, I'm sorry. Yeah, it's a 100 ohm resistor. So what should the voltage drop do with that guy? But what should it go to? We know the collector current. We know the collector current is going to be 1.4 milliamp. The collector current is flowing through that resistor. V is equal to I times R. What's that? 140 millivolts. So what would happen to the voltage drop across my transistor? Kirchhoff's voltage law says the sums of the current in a series branch, and the transistor is in series with that 100 ohm resistor up there. So it means if it's dropping 1.4 millivolts, then the transistor's got to be dropping 11.6, right? I mean, good gracious, these guys here are just so neat. Let me turn my simulation back on. If I can get that. Let's see what I got this thing varying in. Hold on. 1%. So I might not be able to get exactly that. In fact, you can see I'm not. That's the best I can do right there is 25 microamps. So 25 microamps, 31 microamps, 31.4 microamps. That means that guy's going to go up to 3.14 milliamps. I can do that in my head, right? You can just move the decimal point over twice. Then 3 point something milliamps dropped across the 100 ohms. What's that going to drop? About 300 millivolts, right? So my transistor should go up to about 11.7. Yeah. 11.69. But notice I'm going to keep increasing my base current. But always notice my collector current and my base current still maintains a 100-to-1 ratio. Ain't that neat? So once you got that ratio down, then it's just fairly easy to try to figure out what this thing's going to do. It's nothing but Ohm's law. So notice now we're up to 136 microamps, 13.67 milliamps. So what would it cost? What would it cost to cause the the 100 ohm resistor to drop? How much base current would I need to cause the 100 ohm resistor to drop 6 volts? Well, we use Ohm's law. I want a 100 ohm resistor. I want a 100 ohm resistor to drop 6 volts. I is equal to V over R. I would be equal to 6 divided by 100. I would be equal to what? Huh? 60 milliamps. But I'm asking what base current. So IB would be equal to IC, which is 60 divided by beta, which was 100. So what's my base current? What base current do I need? Everybody see this? All we're doing is rearranging a formula. So I got how well you can come up here and use the same thing that you used in DC. So usually we take the multiplication program and we would say IC is equal to beta times IB. And now I've got all my formulas, right? You understand? So what would IB be equal to? IC divided by beta. And beta would be equal to IC divided by IB. So there's your 3 formulas that you can do by rearranging those things without having to do algebra, which is really, really neat, right? So let's see if we can get 600 microamps into my base and see if we come up here. I'm not saying I can because we can't vary these resistors because they're computers, so I can't vary them in an infinite number of combinations. So here, that's 400 microamps, 500 microamps. And I think if I do one more, I'm going to go over that. Yeah. So that's the best I can do, 619 microamps. But notice my transistor is dropping 5.8 volts, so my resistor is going to be dropping 6.2, right? Or I'm sorry, 4.2. So what region are we in? Are we in saturation? Are we in cutoff? Or are we in the active region? This is active. That's exactly right. Because when I'm saturated, when it's cut off, it acts like an open switch, right? Which is where we started off with. Now we're active. The active is where amplifiers operate at. This is where your stereo amplifiers operate, your microphone amplifiers operate. We're operating that transistor in the active region, where I can take a little small base current and I cause the output to change, and then I put another thing out here that uses that change in voltage, right? You understand? So let's increase it. What would it take to saturate it? It takes about 1.2 milliamps, right? But notice, I keep increasing base current. My voltage drop across my transistor is going down, so the voltage drop across that resistor has to be going what? Up. Because Kirchhoff's voltage law says the sums of the voltage drops, it don't say sometimes, it don't say hardly ever. No, it says it always has to equal to the applied voltage. As soon as we get down below a volt, we usually consider this to be saturated, even though I think I can get it down below. So the transistor is pretty close to saturation now. And then once we saturate it, I can keep pumping up the base current. And then it's going to almost have no effect at all on the voltage drop across the transistor. So we're pretty much well saturated. So the transistor is only dropping 117 millivolts, right? Around 100 millivolts, which in electricity or electronics, that's basically nothing, right? So your resistor is dropping about 12 volts, 11.88. Resistors dropping, transistors dropping about about 100 millivolts. So now the transistor is saturated. It's acting like a closed switch. And what's nice about this, if I saturate it, we can control a pretty good deal of current with a very small transistor, because the power that the transistor is dissipating is equal what? To V times I. Well, if V is really low, then I can be what? Really high. So when we operate these transistors between saturation and cutoff, then we can get a pretty good deal of current flow out of a small transistor. Now it's still got current flow through it, right? When we operate it in cutoff, then you got to understand, if I've got enough current, if I got enough voltage, I can push a current through anything. So we have a breakover voltage between the collector and the emitter. If you push current through that thing backwards, then it's going to burn it up. Because you understand, you got a piece of silicon in there, and we got a collector to emitter breakover voltage that we're very concerned with. I was listening to a video and it says it would drop all the voltage no matter what it was, and I said, that guy don't know. Crap. It's going to drop the voltage until we get it up to where it can't drop it anymore, right? And we're going to push stuff through there. It's just like the diode. You know, the diode has a breakover voltage, right? If you exceed the breakover voltage on a standard diode, then it's usually bad. So if you break over a transistor, it's bad. So right now we're operating in saturation. So if I want to turn things on and turn things off, then I'm going to operate it between saturation and cutoff. Now I'm operating it in the active region. So we're going to have two currents. We're going to have two measurements that we're going to deal with. And one of them is going to be called IC max. The IC max rating is the current you can get through the transistor if it is saturated. And then we're going to get a power dissipation. As soon as I have my transistor drop a voltage, then now all of a sudden it's consuming power, right? You understand? V times I. So if we operate in the active region, what we're doing is we're going to be concerned with the power rating of the transistor. If you exceed the power rating of the transistor, then what's it going to do? It's going to burn it up. So saturated, IC max is going to be saturated current. Then the power dissipation is going to be if we operate in the active region. So how much power would my transistor be dissipating? It's dropping 6.8 volts, and I've got 51.47 milliamps of flow through the thing. So when we calculate power, we ignore the base current because it's so small. So how much is my transistor dissipating? Power is equal to V times I, 5.85 volts, 51.47 milliamps. Pretty easy, right? $6.85. I think I can zoom up on this a little bit, but it'll probably make everything just, let's see. No, it's not making the meters bigger. It's making my amps, let me get it, what I'll do is get rid of this voltmeter and put a panel meter down here. Oops, that's amp freaks. I want to put an amp meter in parallel with anything, right? Volts. Make sure we have it set on. This is an auto ranging meter, so we don't have any problem. And it's set on DC. Okay, so now I can blow it up so y'all can hopefully see some of these readings. So the transistor is dropping 6.85 volts. I have 51.48 milliamps flowing through it. So how much power is being dissipated by the transistor?
356.1
milliwatt. If this is a 3904, we just burned it up. It's 100 milliwatts for that transistor, which is the one we're going to be dealing with. So when we're dealing with operating the transistor between cutoff and saturation, we're concerned with how much voltage it can block when it's cut off, right? You understand? And we're looking at how much current it can conduct when it's saturated. When we're dealing with a transistor in the active region, we're concerned with how many watts we're making that thing dissipate. If you exceed the wattage rating on the transistor, then you could burn it up. By the way, what determines the size of the transistors is basically exactly what determines the size of a water valve. It's how much flow you're trying to control, right? So we have different sizes. Let's see if I can find some of these. And these cases have names. Here you go, Michael. We call this a TO3. So most of your transistor cases start with TO for transistor outline, and then they're assigned a number. And the number they're assigned, it has nothing to do with the size. It's what package they were assigning when they got to that. So the TO3 package has been around a long time. Now, when you look at the TO3, you don't see it looks like it's only got 3 leads. But these guys right here produce a lots. So the whole case is the collector. So this whole case is the collector. So when you mount it, you got to make a connection to the what? Collector, and then one of these would be the emitter, and one of them would be the base. I don't know. I have to look this up. I use a 3055, and it's a 115 watt transistor. If you heat sink it. So normally you'll see 3 leads, but a lot of people say, well, where's the 3rd lead? But metal's a good conductor, right? So where's the 3rd lead? It is, huh? It's the metal. Yeah, it's the whole metal. That's the collector right there. Normally, if we're going to expose a junction to the atmosphere, which one would you expose? Would you expose the base? Would you expose the emitter, or would you expose the collector? A lot of people want to say the emitter, but the emitter base junction is dropping almost no voltage at all. That collector junction is reverse bias. All the voltage drop is between on the collector. So if you measure between the collector and base, then the collector and emitter, you'd see that the difference between your emitter and base is only about 700 millivolts. So if it's dropping 5 volts, that 5 volts is being dropped at the collector. So that means the collector junction on a transistor it is the hottest junction. So if I'm going to expose one of the leads directly to the atmosphere, it's going to be the collector. So we'll get into these cases like this. This is a TO22. Now it has 3 leads. Oh well, I crushed my finger this morning. You'll see that. I'm not going to say I did it. It has 3 leads on it. But if I took an ohm meter and measured between one of these leads, one of them would measure continuity to this big nice metal tab that's on it. And I just identified the collector. So the collector is going to be connected to these tabs. Because what we're trying to do is dissipate the heat. And how much heat you can dissipate is directly proportional to how much surface area you expose that to, right? You understand? So, I can't remember what this case is. But I'll pass these around here with my. But sometimes they come in metal cases like this. But what I want you to do is when I bring it around, you look and you'll see one of the leads is soldered directly to the case. Mounted directly to the case. And what do you think that lead that's mounted directly to the case is? That's the collector. Good. These guys are real neat because what they'll do is notice the leads are in a V, right? And we got a little tab, by the way. The tab identifies the emitter. And usually this guy here that's offset is the what? Is the base. And then the collector is real easy to see. And of course, so the bigger the package, the more current, right? IC is bigger, and the more power it can dissipate. This is a TO92. These are the ones that we're going to be using. This case, I don't think it's this transistor. Now the problem with these cases, there's no defined method on which one's the base, which one's the emitter, and which one's the collector. So what we're going to do is we'll show you how to identify. Of course, you can identify it by looking up the data sheet, right? So you look up the part number, and they're going to show you how the pins are arranged on the transistor. But we'll show you how you can identify them with an ohm meter too. It's not hard. So we can identify the base, emitter, and the collector with an ohm meter, which is really, really neat. And we'll teach you how to do that. The method that we're going to use is not in a textbook anywhere that I've seen. And then they keep getting smaller and smaller and smaller. I'll try to pull out a breadboard. A small transistor. And we got these guys right here. These are called integrated circuits. And these transistors are so small that they all put, this guy here might have, let's see what it is. 7486, that would have a lot of transistors in it. This guy here's probably got 50, 60 transistors inside this one package. And it's on a little old tiny circuit that's in the center. And then we call these pins, and we would have to connect these pins a certain way, right? It's just like the transistor. But these guys here don't produce a lot of current. They don't produce a lot of power. And the less power they have to provide, the smaller the transistors can be, right? Y'all understand? So if I looked at the valve on this water fountain out here, it's not going to be very big because it's not controlling a lot of flow. If I looked on the water valves on the one that's controlling, my bathtub, they're going to be what? They're going to be bigger. And if I went out there and looked at the water valve on that water meter that's controlling my house, it's going to be even bigger. Then I go to the water valve that's controlling my neighborhood, it's going to be what? Even bigger. And then I get to the city of Birmingham out there on 280, where they're providing all the water to the whole city of Birmingham and a lot of the metropolitan area. Those valves are going to be what? They're going to be huge. Y'all seen some TVs where these guys are opening and closing the valves with these big old wheels, and you can look at the big old pump out there. That's a big old water valve, right? Of course, it's controlling a lot of water, a lot of flow of water. It controls the flow rate, right? Y'all take a break. So everybody, let's review a little bit. Everybody okay with the symbols? Huh?
I didn't have that.
So I know y'all have access to these PowerPoints, right? Where they at? Or lab over here? By the way, most of the time we draw the symbol for a transistor, we don't draw a circle around it, even though the circle is part of the symbol. You very seldom see it used. It does, and it's hard to draw a circle without some type of template. It's real easy to draw the transistor. So what we have to do, we have to make sure we properly bias. The base to emitter is what? To cause it to operate, the base to emitter has to be forward biased, right? To make it operate in either the active region or the saturation. The base collector junction is what? Reverse bias. And we'll look about a little PNP next class. By the way, the package is not determined if it's a PNP or an NPN. Y'all realize that, right? So we could just as well have a PNP transistor. This could just as well be a PNP transistor or an NPN transistor or a voltage regulator or a triac or there's a lot of things that that can be put in this package, right? You understand? So just because you see one of these packages does not mean it is a transistor. Anything that's electronics that we can fit in with 3 pins is going to be in these same packages, right? Y'all understand that? So how would you know that? Well, you'd need to look at the part number because it's going to have a part number on it. By the way, just about not all transistors, but just about all just about all. Most of the transistors, most transistors start with a designator 2N because there's two junctions in there. So diodes usually start off with what? 1N, because how many junctions are there in there? 1. Most of your transistors start off with 2N. So if you see a 2N on the part number, odds are it's a transistor. Now, don't say whether it's an FET or a bipolar transistor. Both of those usually start off with a 2N. And just because it don't start off with 2N does not mean it is not a transistor. Especially if it's not JEDEC registered. So this is a JEDEC registered package. And so JEDEC is the Joint Electronic Device Engineering Council. And what these people do is they provide the dimensions and everything for this package. And then anybody can do what? Anybody can use it when they make, and that's what's neat when you get into a new science. Everybody wants to share everything, you know. And using standard packaging is okay because now if you have a drawing program that automatically sets out your printed circuit boards for you, like a MotoSim or something or a Multisim or something like that. If you're using a TO3 pack, then all the pin spacing and everything is what? It's the same. They're all the same, whether it's an integrated circuit or what. So most people, when they use packages, they use standard packages. So that means it's a lot easier for people to develop stuff around their package, right? Does that make sense? It's just like most cars use standard size tires. If it don't use a standard size tire, it's fun. You pay a lot of money for them suckers. I see these big old trucks they do on those monster trucks. They was looking at some thing I was watching the other night where they had the rock crawlers. They have specially made tires. They don't tell how much they pay for them tires.
Some of the tires are bulletproof.
What's that?
Some of the tires are bulletproof.
Yeah, the ones they're
Made out of Kevlar.
yeah, but Kevlar is not bulletproof. Might be bullet resistance. There's been people killed using metal jacket bullets. They'll go through them suckers like this. It's like they don't no longer call these watches waterproof. They give you they call them water resistant, right? And they'll give you a certain number of meters that they're guaranteed to keep water out. So the forward bias from base to emitter narrows the base to emitter depletion region, then the base to collector is jerking it apart, right? You understand? And them electrons, when they go through that little old tiny base, they got no option but to do what? They suck toward that collector, but we do have some that go through there. We've already talked about this. Already talked about that. And this shows you the little picture that we've already seen that I drew. This is a lot prettier. We got the symbols. Everybody okay on the symbols? Because when we draw schematics, we don't draw all that garbage right there. We draw the symbol, right? Even though this is the way it's made. Small base current can control a large collector current. Kirchhoff's current law says that the total current entering a junction and has to equal to it leaving the junction. Therefore, the collector current and base current the sum of those two currents has to equal to the what? The emitter current. And then once we've got that, we've got our other two formulas. So here's your formulas right here. Of course, they'll be on the formula sheet, but this is nothing but Kirchhoff's current law. Well, if you knew the transistor and you knew how it operated, then you wouldn't need this formula. And of course, for calculations later on, we're going to say that IC is what? You know what the little squiggly line means? Roughly or approximately. Good, yeah. It's not equal to it, but when I get into calculations, we got so many other approximations that's going on. A lot of times we can use this formula. So if I say IC is equal to IE, true, false, that's going to be false, right? You understand? If I say if IC is approximately equal to IE, that statement right there would be what? True. So watch for that on the test. Saturation, the transistor acts like a what? Closed switch. A closed switch will drop no voltage if it's good. A transistor will drop a voltage. It is not a closed switch. It acts like one. But you saw in our simulation, it was down to around 100 millivolts, right? And when you compare 100 millivolts to 12 volts, you know, that's just not cut off. The transistor acts like an open switch. It is not an open switch. There is current flow through it. It is not an open switch. It is a path current can get through there. But the current flow is so small that we basically can do what? We just ignore it. In the active region, it acts like a what? Rheostat. What controls the size of the rheostat is the base current. And that's all we're going to talk about today. So we're going to continue on. We talked a little bit about beta, but, and look at a little more detail. See what we're getting into. Different ways we can bias it. This is the guy right here for active region. This is the guy right here. Voltage divider bias. And believe it or not, guess what laws we're going to use to calculate that whole circuit? Kirchhoff's law, Ohm's law. And we're not going to use beta at all. But we need to understand just a few little things, and we can solve. You can solve for the voltages. You can solve for the bias voltages in these forms. If you learn DC, you can solve for the biases in this circuit without any problem. If you didn't learn DC, if you had problems with series circuits, this is basically a series circuit. Most people in DC do okay with series. Well, actually, it's series parallel, but we're not. Most people do okay with series. But, when I teach DC, even in advanced classes, people want to calculate everything like series circuits. All right, gang. Let's go to lab.